This is build up your understanding question number 11 from electromagnetic induction from the book Pathfinder. So let us see what is the question. Curved surface of very long hollow cylinder of radius r. This one much smaller than its length. The radius is very small. So you can consider this as almost infinite cylinder is uniformly charged with surface charge density. So on this surface, you have surface charge density sigma. At the center of the cylinder is small insulating ring of radius r and mass m charge q is coaxially placed. So axis of ring, this is ring, axis of ring and axis of cylinder both are same. The arrangement is in gravity free space, so there is no gravity. Now cylinder is given an angular velocity omega naught. So this is the axis. About the axis, cylinder is given an angular velocity omega naught. How much maximum angular velocity will the ring acquire and in which direction relative to the angular velocity of cylinder? Fine. So let us see how do we solve this question. Here, first thing is that which you should know that the long rotating charge cylinder is basically like infinite solenoid. So infinite solenoid also current is like this. There are n turns per unit length and current is like this. Here also current is this way because there is charge on the surface. And then when it starts rotating, charge start moving. Charge moving is basically current. So we can use the formula of solenoid. B is equal to mu naught Ni. Now, N is what? Number of turns per unit length. So I can write this as total number of turns divided by its length and I. Now, what is Ni? See here in solenoid, the diagram of solenoid is something like this. So this is I, this is I, this is I, this is I. So I is the current in one turn. So if you combine all the turns, then total current becomes Ni, right? So total current is Ni and total length is L. So this is basically I'm writing as di by dx, current per unit length, right? So remember this also. Now keep this in mind. We'll calculate the formula of long rotating charge cylinder. Here, if charge cylinder is rotating, total charge is Q. Suppose in this L length, charge is Q. What will be Q? Sigma into 2 pi RL, right? Surface charge density into area. Current will be what? Q by T, right? It's a uniform, it is rotating with constant omega. T is 2 pi by omega naught. This is given omega naught in the question, so I will write omega naught. Now, so this is the current in this L length. What do we need? We need current per unit length. So current per unit length is this. So magnetic field due to infinite or very long rotating charge cylinder about its axis with an angular velocity omega naught is this, right? So this result you have to use at many places in the Pathfinder questions. So it's better if you can remember this. Now, after that, coming to the question. See what happens in this question. The concept here is, thus this is the cylinder. It is rotating. Initially, the cylinder was at rest. Fine. So what was the magnetic field inside? Zero. When cylinder starts rotating with, let me write omega naught here because it's given in the question. So when cylinder starts rotating with omega naught, what happens? There is a magnetic field inside. Fine. And ring is somewhere here. So if you focus on the ring, then initially what was the flux from the ring? Zero. Finally, what's the flux from the ring? There is some flux, right? V into pi r square. So because of flux change, what will happen? There will be one, but this ring is non-conducting, so there cannot be any current. Because of this flux change or change of magnetic field, there will be an induced electric field. This is cylindrical region. You know what is the formula of induced electric field? If magnetic field is changing in cylindrical region, this one, R by 2 dV by dt, right? So this view, if you see, then cylinder looks like this. It is rotating this way. So this is the current and that's the ring. Now, because since cylinder is rotating this way, initially there was no magnetic field. Finally, there is a magnetic field. There is a change in magnetic field. Whenever there is a change in magnetic field, there will be induced electric field. So induced electric field, you know, in cylindrical symmetry cases, it is circular, right? Tangential. So this is the direction of induced electric field. It will be opposite to the direction of omega naught because magnetic field is the changes. What is change? Changes from zero to some value, right? So it is increasing. So it will try to oppose it. So this is the induced electric field direction. Since ring is non-conducting, but it has some charge on the surface, which is given Q. This force, this electric field will apply force on that charge, right? Here force is in this direction, here it is in this direction, here it is in this direction. So net force is zero, you can see from the diagram. It's very clear, but there will be net torque. That equation I have written. torque equal to I alpha. So what is torque? Torque is QE, total charge is QE into R. R is this radius of ring. This is equal to I. I is for the ring about its axis is mr square alpha. Now E is this. So I've written E, one R I have cancelled and written E. Then one more R cancels and you get this equation. Alpha I have written as d omega by dt, right? So dt cancels, and now magnetic field, change in magnetic field, final minus initial. Initial 0, finally what's the magnetic field? This is the magnetic field. So that is what I've written. And initially omega was 0, finally omega is omega. So the value of B I have substituted from the previous result, and then if you integrate both sides, you get this as omega, right? So again, a very, very good question, standard question for JEE Advanced. And this question again with a little bit of modification can come in JEE Advanced. So if you have understood something, if you learned something, please like this video and please subscribe this channel also with your friends. Thank you very much. Thanks a lot. We'll meet again.